Alrighty, folks. So today we're going to be talking about section 9.3, which is about comparing two population means again. And this time sigma is still unknown. And we're going to have dependent samples. All right, so we've talked about that the past couple of sections. This means that there's some way that we have that pairs our data, right? Either it's the same individual giving two different, or taking the test at two different times. Maybe we've just made some arbitrary pairs for our study. Maybe we're doing something like looking at twins, and we've separated them into two groups to be our two samples. However they're paired up, dependent samples means there is some way to associate each point of data in one sample with another point of data in the other sample. So we have a little bit different nomenclature here. Here we're going to be talking about we're going to have our point estimate is no longer just the difference of means of the samples. I can write an M, I promise. So our point estimate is going to be something called D bar. And instead of being the difference of means, this is going to be the mean of the differences. Right? So it means we're going to sum up all of the paired data, right, and divide by the number of pairs. Right, so n equals the number of pairs. This is still sample size. Right? It's just that both samples are going to have the same size, so we don't have to call it N1 or N2 or something. If every piece of data on one list matches up with another on the other list, then you've got to have the same number in each sample. So the sample size is going to be the same thing as the number of pairs. Right? So our point estimate is D bar. And our confidence interval is still going to be this guy. Right? It's still our point estimate plus or minus E. E is now going to be T sub alpha over 2 times S sub D, and we'll define that in a second, divided by the square root of N. The degrees of freedom, because you have to have it every time there's a T, is N minus 1. And SD is going to be the standard deviation of the differences, right? So if we recall from our formula way back at the beginning of class, that's going to be the sum of all the DIs squared all over N minus 1. Right, so let me be a little bit more clear here. The DIs are just the difference in the pairs. So there's going to be a little bit more setup work on problems like this. We're not going to get to just plug it into, get the data from the word problem and plug it into the formula. We're going to need to get the data, do some stuff with it, and then plug it into the formula. So your calculator can do this. It's a little bit more complicated than just throwing something into the same command, but the book walks you through it. Again, I can't do it because the app's not working on my iPad, but the book has some step-by-step instructions there. And if you have questions, you can always ask during office hours, and I'll figure out a way to work through it. Maybe we can have, if we do a Zoom call, or if you're in person, then you can show me your calculator and I'll tell you what buttons you need to press to get to what you need to do. But that works a lot better on one-on-one, and it doesn't work here when I can't show you anything like that. So we're going to work through some problems. I again have the t-distribution table, so that we can look some stuff up there. And I have a couple problems down here. I'm going to pull the first one. Oop. I'm going to pull the first one from the correct layer up so we can work on it. And then I'm going to pull the second one down so it'll be out of the way. So, first one, we're testing the effectiveness of a particular piece of software that purports to help with vocabulary training in foreign languages. You give a vocabulary test to a collection of 6 students, then they're supposed to use the software for a month, and then they take the test again, right? So this is an example of a common way that you get paired data is you have a before and after test, right? So these are the same 6 individuals, right? This is person 1 took the test before they used the software and got a 75, and took the test after they got the software and got a 79. And then, of course, it's person 2, person 3, person 4. So these are paired by being tests taken by the same person, right? That's why they're paired. It's not just because we have the same number. If you remember from last section, we had the same number of hotels in the second example, but those hotels had nothing to do with one another, right? Here, these are matched up by the same person, took both of these tests, just with something happening there in the middle, right? So let's find all our DIs. So we'll call this person 2, this is person 3, person 4, person 5, and person 6, right? So that tells us that n equals 6 for 1, right? We have a confidence interval, and we're told an 85% confidence level. So 85% equals C, 0.15 equals alpha, in case that comes up. So D1, right, the difference, let's go after and then before. I have it written up like this. We'll do before then after, right? So that's going to be 75 minus 79, so it's going to be -4. D2 is going to be 68 minus 78, so that's going to be -10. D3 is going to be 71 minus 74, so that's -3. D4 is going to be 90 minus 89, so that's 1. D5 is going to be 55 minus 55, so that's 0. And D6 is going to be 42 minus 61, so that is -19. Right, so D hat is going to be what we get when we add all these together and divide it by n. So it's going to be -4 plus -10 plus -3 plus 1 plus 0 plus -19 all over 6. So that is, let's see, 14, -14, -17, -16, -35 over 6. So let me figure out. That is 5.833. Technically that 3 is repeating, but we're probably just going to round it off there. right? Oops, negative that. So that is our d bar. Now next we need to find s sub d. And this is going to be fun and exciting, right? So this is the sum of di minus d bar squared. Oops, all over n minus 1, and then we're going to take the square root of all of that. So this is going to be negative 4 minus negative 5.833 squared plus negative 10 minus negative, which turns it into a plus, 33 squared plus negative 3 minus negative, which turns it into a plus, plus, and we're not going to have room. Let's make this smaller. That needs to be about half the page. There we go. Let's see if I can match that smallness. 1 minus negative, and then square, plus 0 minus negative squared, plus negative 19 minus negative squared. All of that's going to be divided by 5. And then we're going to take the square root of it. The other thing we could do, of course, is we could bring up a spreadsheet. We could put all of these d's in it. That is, in fact, what I'm doing right now to get this value. So I put d's in it. So negative 4, negative 10 in the next cell, negative 3 in the next cell, 1 in the next cell, 0 in the next cell, and negative 19 in the 6th cell. And then I want to set this equal. I want to find the standard deviation. And I need to remember that standard deviation is the sample standard deviation, right? Because there's lots of standard deviation options if you're doing a spreadsheet. We talked about this way at the beginning of class. There's lots of different options if you're doing the spreadsheet. P is the one that means population. Standard is the one that means sample. So I'm going to put in my 6 values there, and it comes up with 7.521. And again, that's approximately, right? So you could do that by hand, you could fill all that out, or you could use the tricks that we learned at the beginning of the semester, which include plugging them into a spreadsheet and using the standard deviation command on the spreadsheet to figure out what it is. And then, now that we have those guys, we can find E. Our formula for E was T sub alpha over 2 times, oops, that's weird. Oh, I see. I mean, I don't actually see, but it's fixed now, so we'll move on. Speaking of being fixed, okay, good. Thank goodness. Times s sub d all over the square root of n. So that's going to be t sub 0.075 with, we haven't figured out degrees of freedom yet, but I've got some nice space right here. We said degrees of freedom was n minus 1, so that's also 5 times 7.521 all over the square root of n. So let's figure out what that t value is. Our subscript is 0.075 and our degrees of freedom are 5. So here we have a problem, and it's that I don't have the table that I thought I had. So we're actually going to change this. We're going to change it to 80. We apparently just don't care how accurate we are on this. So that means this is 80. This is 0.2. So apologies for that. I just sometimes forget that I don't have quite as nice a table as I want. So this is going to be 0.1. So we look on the chart, 0.1, degrees of freedom, 5. So degrees of freedom is over here. And look over here. 0.1 is here. Look down here, and they meet at 1.476. Oops. N was 6. So then I go to my calculator. I plug in 1.476 times 7.521 divided by the square root of 6. And I get for that 4.532, roughly, approximately. Right. So my confidence interval, we said before, was my point estimate minus the error, my point estimate plus the error. So this is going to be negative 5.833 minus 4.532, comma, negative 5.833 plus 4.532. So let's see, that's going to be negative 10.365 on one side, and it's going to be negative 1.301 on the other side. Right, so here we've gotten a situation where it's negative on both sides, right? And that means, again, this works the same way as the difference of means before, even though we've got a way different process, right? So both of them being negative means that the second one, being the one that's being subtracted, is the bigger one, right? So if we look back up here, this column, the second one's being distracted, was the after column, right? So that tells me we are 80% certain that test scores are higher on average after using the software. Right. So after using the software was the ones that we were subtracting from it, and they're going to be bigger if the difference of means is negative. We are 80% certain that the difference of means is between these two numbers, and if that's the case, it's negative. So therefore, we are 80% certain that the test scores are higher on average after, because that was the column that we were subtracting from the other column. Right? Okay, so let's do this guy. Pull it up here so we have all the space. So here we have a double-blind study, was constructed to evaluate a new medicine. Each of the 10 volunteers was paired up, and one of the pair was given a new medicine and the other one was given an old medicine. The length of their illness was recorded for each person, and we want to evaluate their effectiveness compared to one another. So this is another way that we get paired data again. It's where we split our sample in half and did one thing with one sample and another with the with one half and the other with the other half, and we just matched these up arbitrarily, right? We just made sure that there was something that hooked it up to another one, right? We set them off in pairs, and then gave one of each pair a different thing, right? So there's nothing directly connecting the individuals except for how we constructed our study, right? So we're going to call this 1, 2, 3, 4, 5, right? We've got 5 pairs, so n is equal to 5. Flat out tells us that alpha is equal to 0.01, which means our confidence level is 99%. And so let's get going. D1 is 4 minus 5, so that's -1. D2 is 7 minus 6, so that's -1. D3 is 5 minus 6, so... Oh, no, sorry. Something was wrong there. That's a +1, usually, when you subtract 6 from 7. That gets us a -1, though. D4 is 3 minus 6, so that gets us a -3. And D5 is 5 minus 4, so that gets us another +1. Right. So D bar is going to be the sum of all the DIs divided by n. So it's going to be -1 plus 1 minus 1 minus 3 plus 1 all over 5, which is -3 over 5, or -0.6. Right? So, yeah, that works out, right? So next we need to find S sub D, right? Because we know that's going to be involved in our E. So we might as well figure that out before we get to anything else, right? This is the square root of the sum of DI minus D bar, all that squared, all over n minus 1. Or my other option is to go back to a spreadsheet, and I like that one personally much better. So I'm going to do that. I put my first number is going to be -1. My second number is going to be 1. My third number is going to be -1. My fourth number is going to be -3. -3. My fifth number is going to be 1. And I get from this 1.673. Yeah, okay. So we get that for our standard deviation. So that means that we can go ahead and start to find our E. That's going to be T sub alpha over 2 times S sub D over the square root of n. So that's going to be T sub 0.005 times 1.673 all over the square root of 5. T sub 0.005. Oh, we also need to know the degrees of freedom. That is always n minus 1 for these problems, so it's 4. So we're looking at degrees of freedom 4 and subscript 0.005. Degrees of freedom 4 subscript 0.005, we get 4.604. So 4.604 times 1.673, all of the square root of 5. So we go to our handy dandy calculator. 4.604 times 1.673 divided by the square root of 5. And we get 3.445. So our interval, which is d hat minus e, d hat plus e, is going to be negative 0.6 minus 3.445, and negative 0.6 plus 3.445, which is negative 4.045 and positive 2.845. Right? So here we have one where it's negative and then positive. Right? So if we recall back to section 9.1, this means that we do not have any evidence to claim, or rather, it's really enough evidence. Right, so we don't have enough evidence to claim the two treatments reduce the lengths of symptom showing differently on average. Right? So the trick here is that 0 is inside of that interval. So it is very possible that the difference in the average length of showing symptoms for these two treatments is exactly the same. Right? And because it is very possible for that to happen, we don't have enough evidence to claim that they work any differently from one another. Right? There probably studies need to be done on more than 5 people per treatment. That's one of the problems that we had here, right? Was that our T sub alpha over 2 was so big. But I also didn't want to have to go through finding D by hand or D hat by hand for more than 5 people. But since 0 is in that confidence interval, we do not have enough evidence to say that these two samples averages are significantly different. And so that's what we have here. Right? Remember, when 0's in there, we don't bring the confidence level into it. Right? Because we haven't shown that 0 is in there. We haven't shown that it's definitely 0. We've shown that 0 is a very possible answer for it. And that is all that we can show from this. So we don't have enough evidence to claim that they're different. Right? So we have one more confidence interval section, and then we're moving on to hypothesis testing. But that's later, and I'll see y'all then.